Hello everyone, welcome to this masterclass from Flavio from leboncoin and Olivier from Doctolib. Today we will be talking about PostgreSQL, or PostgreSQL, sorry Flavio, and how to understand PostgreSQL plans and how to use those to make performance queries, choose what indices to create, how to build a performance schema. This presentation will last an hour and we will have 15 minutes at the end to answer questions. So please, you can ask your questions in the comments during the entire presentation. And at the end, I will do my best to maybe group them, maybe choose them. I will do my best. I think that is all. So Flavio and Olivier, the floor is yours.
All right, thank you, Victor. So good morning, everyone. And so I'd like to first, before we start diving into the topic, I'd like to share with you a little story that explains how important is it for me to understand how works the tool that we are using every day as a developer or engineer. And some of you may know that I've been running a bakery for the last decade. And besides my engineering education, I had to be trained as a pastry chef. And being trained as a pastry chef is quite different from being trained as a bread baker. And so at one point, we decided to make bread, obviously. And so I got a recipe from a friend. I was not trained for it. And so I applied the recipe step by step. It worked pretty well for quite a while, until one day it started not working as usual. And so everything stayed the same. The recipe was the same. The ingredients were exactly the same, obviously, and we didn't change anything in the process. So the mystery started. At one point, we quickly realized that we didn't know much about bread. And because we didn't know what was going on, there was no way we could fix the issues. So I had to call a friend, and after a couple of days, it fixed everything, hopefully, for the business. And so what was going on under the hood was we needed actually to adjust the amount of water according to the flour harvest, to the flour and room temperature and the humidity level. And we also needed to monitor the pH level. Who knows? So we learned a lot of things along that journey, and that's why we strongly believe with Flavio that we need to give you all the keys. Some keys, so you can understand what's going on under the hood with PostgreSQL. All right. So in this presentation, we try to cover those topics: the data structures, the scan methods, the optimizer and loading issue, and some other more specific topics about hash, join method, and others. All right. So first chapter. So I didn't say it, but at the end of the presentation, we won't have finished with the topic. It's a big topic, and so we will only address a part of it, okay? That would be our first presentation together. So let's talk about the heap, the pages, the basic command to get the query plan explained, and the three most scan methods commonly used by Postgres. All right, so what you can see here is a page on the pict. So the page is it's always a fixed size. It has a header, and on top of it, and it's like a small book, and you have the summary, and the summary points to the actual data on the bottom of the page, going backwards. Most pages, they contain data, text, and images, and some other pages, they are just for indexes. So indexes, they are also stored in pages. And you can see a table just as a collection of pages. That's pretty basic. Next slide, please. So here, what we can see, and you probably heard about it, is what we call the heap. The heap represents the aggregations of all users' data. In this example, we have two tables, A and B. What you can see is each data for each table is going to be stored in a dedicated data files of 1 GB. And so table A has 1 data files, table B has 2, and each of the indexes that we create for table A and B will be also stored in the dedicated data files of another gigabyte as well. And the heap, as you can see, is the conceptual representation of all the data files next to each other. And so it's going to be an optimized space for sequential access and index lookup. So Flavio, by the way, so can you explain us why do we need such a thing as a query plan?
Yes, thank you. Why we need a query plan? Because there are several ways to retrieve data from the indexes, from tables. Sometimes we have to join tables together to get results. Sometimes we make subqueries. There are several ways to retrieve those data from the files that we laid out on disk. And so we have to find the optimal way, or the best way, or the cheapest way to retrieve those data as fast as possible and using less resources as possible to the user in this, or the application in these cases. So there are, for example, here we have a query with where clause, where we have some parameters that we want to say to the database to retrieve data to. So that's we will try to explain you how Postgres tries to decide which plan to use to retrieve those data from the disk as fast as possible. So back to you, Olivier.
Okay, so let's explain the most simple plan. Okay, so in this example, we'll take so you can see on the left, we'll do a select on the one column in the table called PG class. Okay, so in order to see what's going on, we'll just put the word explain before the query, and we'll get that result. The first thing that you see in the result will be the scan method, the access method, actually. That's how it is called. So the access method chosen to get the row in that table. Then right after, you see in parentheses something called the cost that we will explain in detail right after, with 2 numbers, okay? And so this is an estimation. This is not something actual, but this is an estimate. And right after, we have also an estimate about the number of rows to be returned, not the actual, but what Postgres thinks is going to return. And right after, the last thing will be the width of the average width of each of the rows to be returned by that query. Okay? So Flavio, could you tell us, could you explain us what is the cost, please?
I'll try to. A query plan cost is a way to Postgres to decide to put some numbers on it, so we can try to find the best one, and that will be the cost that is less expensive to retrieve data from the disk. How is it calculated? So we have a normalized cost in Postgres that is what we call the cost to retrieve a page on disk. So if we have to just make a small program in any language you want and to read 8 kilobytes of data from the disk, in Postgres, that's what we call 1. This is the cost of 1. So if I have to scan 10 pages, the cost will be 10. That's how Postgres decides the cost. And there are some other different costs that we'll see in the next slide. But just looking at the query plan, in this simple query plan that we see here, we have 2 costs there. The cost in the left as 0 is the cost to retrieve or to fetch the first row and show it to the user. So when you make a query, there is a starting cost to retrieve the first row and show it to you, give it back to you. And the second number at the right, 108 in this example, is the total cost to fetch and give you the total rows that will be returned by your query. So that's approximately how Postgres will try to calculate the cost and make decisions after that.
Okay, cool. Thanks for this explanation. Okay, so what we can say on top of the cost, without going too much too deep into the details, is that the cost, it's a computation. So the computation of that cost is going to be different depending on the access method. And it is based on a set of constants that you can see here. Those constants, they are stored in a file called PostgreSQL.conf. And each of these constants define a cost of accessing pages and processing rows. The funny thing is that you can change those values during any, inside your session, and just doing the set, the constant name equal the value, and you'll get a different cost calculated. All right, so this time we'll do, on top of the explain command, we'll do an explain analyze command. And that command is going to give us actual times. So remember that the explain did not execute the queries. It was all about estimating what was going to happen. This time, we are going to do the same thing. So the plan is going to stay the same. So the access method, is, as you can see here, is still the same, even if we didn't describe yet what was a sequential scan. But so the access method stays the same, but we will execute the query on top. So here, what you can see on the right is the actual times to start. So the first number would be the actual number of milliseconds. So it's 0.0443 milliseconds. It's not a lot. To start the time required to start fetching the first query. And we need 28 milliseconds to fetch all the 3,261 rows. Okay, and on the left, you can see the sum up, let's say, with the planning time required by Postgres to see, okay, to determine what's the best way to return those rows, and the actual total execution time. So now we've just told you about explain and explain analyze. Now Flavio is going to explain you what is a sequential scan.
Okay, so sequential scan is the simplest methods to access data in Postgres, and I'd say the simplest method of accessing data in flat files at all. So if some of you have already coded a file read in any language, any programming language we want, when we use to read a flat file, we just scan the file from the first byte to the latest byte. So it's quite easy to code, it's quite fast, and it's quite efficient. But of course, there are better ways when you don't want to retrieve all the data of this file. So in this case, the sequential scan is very efficient when we have a large portion of the file to read. If I have all the file or a large portion of this file, it is and it will always be the fastest method to access data in a file. So all we do in Postgres is to read pages in sequence. So as Olivier told you before, the pages are 8 kilobytes blocks of data in disk and in memory. And when Postgres will have to scan a file, it will just read 8 kilobytes every time till the end of the file. So we go from the beginning, and then we read all pages and all rows in the table file through the heap. That is a heap in Postgres is what we call the space where we store data on disk. So that's the sequential scan. When the sequential scan is very efficient, as I told you, is when we have to read a large part of the file. In this case, we just make a very simple query, is a select first from names. There's a table called names. And when we don't put a where clause in the command, we will retrieve all the lines, all the rows from the table. So we will scan the whole table. from the beginning to the end. So in this case, in this example, this table has 3 pages. Each page stores 2 rows, and then we just Postgres will just load the first page, read all the rows inside this page, read the second page and all the rows, and read the third page and all the rows. So we have all the rows returned to the user. This is very efficient. I just have to read the whole file and return it to the user. It's very efficient and very fast. When we want just a small part of the table, like this, in the same query with a where clause, where I put ID equals 30, it will return, as we can see in this simple example, we will return just 1 row. So this is not efficient, because Postgres will sequentially scan the first page, the second page, the third page, and will return to the user or the application just 1 row that is a part of one of the pages. So this is not efficient. This is a waste of resources and a waste of time.
Yes. So that's it. This is why we have different kind of access methods. An index. So now we're going to talk about the index scan. In this example, we still have the same table, and from that table, we decided to create an index on the ID column, which is kind of the primary key, let's say. And so we are building that 3 structures that you can see on the right side of the pict, which is called a B tree, but it does not really matter to explain in the detail for the examples what it is. And as you can see, all the leaves, they point directly to the corresponding data rows location inside the page, the data pages. And so, for example, Bob will be pointed by the second leaf on the bottom. And if we now, so what you have to keep in mind too is each time you insert a new record into your data table, like you create a new row, then we also need to insert a node somewhere at the right location inside that index. So let's take an example for a search within an index. Thanks. And so in this example, we're looking for the for an ID. Actually, I mean, there is a small mistake, equal to 30, not less than, but equal to 30. And so we'll start on the root on top, go to 15, and look. Then we go to the branch level, and then we know that 15 is lower than 30, so we just have to go to the next node, which is 20. But the next after 20 would be 49. So we know that we can go down to the leaf level, and from that level we can easily find 30. So in a couple moves, we'll be able to find any value. And this example is only for 6 distinct values, but even if you have 1 million or 1 billion rows, it would be a matter of maybe 10 or 20, 30 values at most. It's a logarithmic search. So this is extremely efficient when you need to return a few numbers of rows rather than a large set of rows. So Flavio, now we just saw that the sequential scan was efficient at returning large sets. The index scan was efficient at returning very few rows. And what if we need something in the middle?
Yes. In this case, there is an access method that's called bitmap index scan. So when we have a certain number of rows to retrieve in the table pages or index pages, sometimes neither the going to directly to a sequential scan is efficient, neither going to the index scan is efficient. So we need to put those pages in a kind of table of matching rows that matches the conditions that you want in the where clause. So in this case, we will try to fetch the corresponding rows and put it on a memory area that's called a bitmap. The bitmap is just like the name says, is a map or a table of bits where each bit corresponds to a page in the table. And we would say if the result we want is present on the table, we put like a bit 1, or if the page is not present in the result, we put a bit 0. So it's quite efficient, quite fast, and quite small to map all the rows of or the pages of the table that we want in the result, and we put that in memory, and it will use a small amount of memory when each byte corresponds to 8 rows of 8 pages of data in the table file. So it's quite fast, quite efficient, and it's very adapted to intermediary results where we have a certain quantity of rows to return to the user. And if we have here an example, like we make exactly the same select in the table names that we showed in the example before, and we put 2 conditions, like created that equals 2011 or created that equals 2021. There are 2 conditions here, and we have to merge them together. It's the OR operation in Boolean. So how we do that? We will look up an index, for example, and we won't load all the data. We will load a small part of this index, so we put that on the bitmap. We will just use a small memory area where we say which bits are on, and when these bits are on, the pages have corresponding values. And we do the same in the second step, and we put in the second bitmap. So there is the first bitmap is the red one, and the second bitmap is the blue one. Those bitmaps are stored in RAM when we have enough space, otherwise we can put that in temporary files on disk. There are small temporary files on disk. And then we make the OR operation between 2 bitmaps. It's a quite fast way of doing that in programming C or any programming languages you want. We just compare both bytes and we make the OR operation, and we have the results of what matches. And with the matching results, we will re-scan the corresponding pages on the table to return data to the user. It's quite simple, but when we say like that, there are a lot of steps to do that, but actually the underlying workings are very simple.
Okay, great. So what did we learn so far? So we talk about the data structures, essentially the pages and the heap. And we also explain you the explain and explain analyze commands. So don't forget to see, just keep in mind that the explain is all about estimate, and the explain analyze will be the actual times by running the query on top. And we thought together the 3 most used and common access methods that Postgres use all the time: the sequential scan, the index scan, and the bitmap index scan. So now we talk about a little more about specifics of Postgres and the role, in particular, about the role of the optimizer and the bloating issue. So Flavio, let's start.
Okay, so what is the optimizer? How it produces query plans? And every time you shoot a query to the Postgres server, we have 3 steps that are mandatory for all queries that manipulate data. So we start with a parser. The parser will look to your query and returns if the query is syntactically correct. That's what we call the lexical analyzer. And if the query is correct, it will generate what we call a parse tree. The parse tree will look of actually the parser will take all the keywords of the SQL language and take the name of tables and columns of the tables, for example, and make a tree of what objects you want returned in your query. So it will also say if the objects exist. For example, if you put a name of a table that doesn't exist, it's the parser that will return an error. if you made a mistake in your query and you put a bad keyword, it's the parser that will return the error for you. So the parser is quite fast, and it's the first step when we will have an error or go to the next step. If your query is syntactically correct and all the objects exist, we will go to the second step, is the planner or optimizer. And the planner will do exactly what we are talking about in this presentation. Actually, based on the statistics of the data distributed on files on your disk, it will calculate the costs that we are trying to explain to you, and is the role of the planner to choose the best plan to execute the query. So if something is going wrong and you have a bad plan, it's this step that you have to look for. And in the next step, the last one, is the executor. It will take the query plan that was generated by the planner and literally run it. It is the role of the executor to know all the access methods to retrieve data from the files or the memory and give it back to you. So after the executor is usually the step that takes more time. Not always, but usually is the step that takes more time. That's why we have to show you in the explain the planning time and the execution time. So we know which one is taking more time. And in the end, you have the results of your query. Some queries don't have a plan. For example, if you try to create a new table, modify a table with alter table, or create indexes, those queries have no plan. So we just go from the parser to the executor. But all the select queries, insert queries, delete queries, all of them, and update queries, all of them need a plan. So that's why we have the 3 steps for all those queries.
So now let's take an example of how the optimizer works in real with the choice of access methods. So we'll take again this PG class table and do just a select on it. As you can see, most of the rows being returned start by P, which is kind of normal considering we're talking about Postgres. And we have like other letters, A, B, C to Z, whatever, in less with a distribution lower for these letters. So what we are doing, we are creating a temporary table called sample, just with the first letter of, so it's basically a copy of PG class, but only with the first letter. And in that table, we'll insert 5,000 of more P, okay, because we need them. At the end of it, just look at the right side of the peak in green, we have a small query that is running, that is showing the distribution of the data. So what we have inside that table is 6,138 P's, okay? So it's about 75% of P rows in that table. Just 1%, a little bit less than 2% of A, which is 138, and just 9 rows of B, 0.1%. Okay, so the distribution is very different for those 3 letters. Okay, so we'll use those. So we'll do some selects on the P, A, and B to show you what's going on. So at first, when you explain the plan, which is like select letter from sample where letter equal P, A, or B, we'll get, surprisingly, 3 times the same plan. And this is normal at this stage because we created in the session a temporary table, sample, and at the moment, Postgres did not yet analyze the tables, so it didn't have any statistics on it. So it just chose what it thinks is best, which is in bitmap index scan. But as soon as you feed Postgres with the data it needs, by running the analyze commands and the name of the table, and we run the explain again for those 3 letters, the P and A and B, then things are totally different. So the P, because of the 75% distribution, will be scanned using an index, a sequential scan. The B the B will be, because there are only 9 rows returned, will be an index scan. And because of the 138 to be returned for the A search, then Postgre decides to use an index, a bitmap index scan. Okay, so this is showing you how the optimizer is actually working. So would you sum up for us the what kind of decision the optimizer takes, please?
Yes. So we saw right here at this point how to scan tables based on statistics that we have, how we choose the best access method, and how to choose best order amongst methods, because we have sometimes to use several methods. So that's what we have at this point. So there is a problem when we store data in flat files, is that sometimes the files will bloat. What's that? Postgres wants to retrieve the data as fast as possible, as we told to you, and with less resources as possible. And then we have a data map of the content of the pages on the heap. So it will depend on how the data is distributed inside the heap, inside the flat files that we have. And when we use to read pages sequentially, it has a cost. And when we do that randomly, it has another cost. It all depends on how fast your disks are, if the data is distributed on disk or in RAM. So there's a lot of importance on knowing how the data is distributed. That's why we need a map to show us where the data is. So sometimes we have the bloating problem, is that when we modify data inside the table. So when we do updates or deletes, we have new versions of the rows, because there is one thing, is that databases are ACID compliant. So we have concurrency between transactions. We have 2 or more transactions running in parallel. And when one transaction makes modifications in data, the other transactions have to see the data before these modifications were made. Exactly when we make like a commit, like we say to the Postgres, this data is now really modified, then the other transactions will see them. But before we say that to Postgres that the data is really modified, the old data has to be visible to the other transactions. That's why we have several versions of the data inside the table. So when we make a delete, for example, in a row, we will not really delete the row from the table. Actually, we will say to Postgres that we are going to delete the row. And then for my transaction, where I am running right now, the row is already deleted. But for the other ones, it's not. So that's why we have to mark the row as unavailable. For future transactions, we say to Postgres, mark this row as deleted, and we put a transaction number on it. And for all the transactions that come before, we will already see the rows. But actually, for the new transactions that came after me, they will not see this row. So this is why we have to keep old versions of the row inside the table, and we call that tuples or dead tuples. And when we do an update, and this is the worst, because we can make several updates on the same row, actually, we won't modify the data in place. We will create a new version of the row. So it's like a new insert. And the old version of the row is deleted or marked as deleted. So if I make 10 updates in the same row, I have 10 new versions of the row inside the table. And when my transaction finishes and all the transactions that came before me are finished, those rows are useless. And that's what we call dead rows. They are dead. They are occupying space inside the flat files that are the tables and indexes, but they are not freed up immediately. They keep in place.
All right. So if the page is bloated, then so the heap. So let's take an example. Let's imagine that you have like you have a table, and that all the rows are spread on 8 megabytes. So 100 pages, because one page equals 8 kilobytes. So at first, at T0, we have no bloating. We just like have new data. Nothing happened yet. And it's 8, so it's 2, 4, 6, 2, 8, it's 10, it's 12, sorry, it's 12 pages. Yeah, okay, well, so let's assume it's 100 pages, like I said. Then later on, there was a lot of updates, deletion, whatever. So it was going live, and that table increased in size because of that, because of the bloating issue we just talked about. And the bloating rate reaches 50%, which is a lot. So it's and when I say 50%, it means that now the size, the physical size within the data file is twice as much as before. And you can see all the red spots where we have dead rows or dead tuples. So now, if Postgre needs to do any sequential scans at one point on these tables, it will require Postgres to read twice as much tables as before. So your performance is divided by 2, basically. So it's so the bloating really slow down your processing time. So keep that in mind, okay? And so the more dead rows you have, the more pages you will have to read, okay? And the effect is also noticeable even on indexes, but at a different level. Okay, so now we have that bloating issue. Is the space dead forever, Flavio?
No, it won't stay dead forever. So we have some tools that will help us to get rid of the dead space. And how it works is the vacuum processes, and it's used to reclaim that space. So what's the vacuum? The first one is the most important one, is the vacuum. That is a command, and sometimes we can call that concurrent vacuum because it doesn't lock the table while it's running. It just makes a lot of input, output, and a lot of I/O in your disk, but it's not actually blocking. And it will not compact the data. It will not actually reduce the size of the flat file, but it will reclaim all the space that is dead. So it will scan your table for dead rows, for dead tuples, what we call in the Postgres jargon, and it will just free up this space so new transactions can use this space. So it will not defragment data, it will not compact the table, but if you run that regularly, you can control the bloating because the space will be reused by new transactions. It's not bad on database that have a high workload, a high modification workload. And then if you do vacuum frequently, you can control also the amount of I/O you will be doing in your tables with your sequential scans and other bitmap heap scans that you like to do. And actually, Postgres does that automatically for us with a process that is called the auto vacuum. And sometimes when we go to lists on the internet, on discussions like in Reddit or other Stack Overflow, people will talk about auto vacuum. And sometimes people say that's a bad thing because when auto vacuum works on a table, you have a lot of problems, etc. Actually, it's the contrary. The auto vacuum is very, very important, and it's there to keep your tables and your database size under control and make your database faster and optimal. So do not turn it off. Do not try to kill vacuum processes. You got problems. It's there to make it better for you. And we have yet another type of vacuum is the vacuum full. And this one will actually compact the table. So if you have, like in the Olivier example, if you have a 50% bloated table and you run a vacuum through over this table, it will reduce the size by 50% on disk. But during the operation, it will lock completely the table. The vacuum through is a blocking process. So it's not made automatically by Postgres because it's not necessary. But when you have a lot of bloat because the auto vacuum is not fast enough, for example, or you misconfigured the auto vacuum, you will need maybe to run a vacuum full by hand. Useless to say that by using it on large tables, it would take a lot of time to run with the table blocked. So be aware that you can have a downtime in your application if it's not made to handle the situation. We have also the cluster command that is exactly, and it works internally exactly as a vacuum full, but it will put your data pages in the same order of an indexes. For example, if you have an index by ID, in an incremental ID, and you run the cluster command over this index, the table will be ordered exactly as this index, from 1 to n. And if you have bloat problems in indexes, you can use the command reindex to control the problem in your index. And since Postgres 12, we can do that concurrently without blocking the index and the table for write. Before Postgres 12, we used to create a new index concurrently that it was available since a very long time. And after the new index constructed, we just dropped the old index and renamed the new one with the same name. But today, since Postgres 12, we just reindex concurrently, and we are okay with that. So that's how we control aggressively the bloat. But if we want to control the bloat without actually blocking things, we just rely on the auto vacuum daemon. It does it for us.
All right, so let's recap what we learned so far. So the query optimizer is the brand for query plans, so you get that. Then a good query plan will provide a plan with the fastest access to data. The optimizer makes decisions based on statistics. The analyze commands gives Postgres the statistics it needs to perform queries in an optimal way. The update and insert SQL commands bloat tables over time and slow down your queries. And the vacuum command helps you mitigate the bloating issue and can reclaim the data space in multiple ways. Okay. So now let's dip into the last part of the presentation, which is about join methods and join orders.
So just a small note, because I know that at Doctolib, people use to make the first syntax when we join tables, like we use the on clause. So we put a select on a table, and then we join the table 2 with the table 1. We use the on clause to say which columns should be joined together. If the column names are the same, we use the syntax using. It's just the same thing, but with a different syntax. And when you write queries by hand, it's faster to type. But it's exactly the same thing, just for you to know in our examples. So let's get it on. Here is an example of a hash join. If you want to make exactly the same query in your local database, you can download the example database, which is Pagila, and the address is in the presentation there in GitHub. You can download it for free. There's no license attached to that, and then you can use that for your testing and your exercises. So in this case, what I did, the Pagila database is like a video rental system from the 90s, when we used to have that thing. And then there is a list of films, movies, actors, and a lot of other interesting information about the subject. And then here, in this query, I want all the names, the first names and last name of all the actors that worked in a specific movie. And I know the ID of the movie, so I will make this query simple for the example. I know that the movie ID is 1. So I just joined the actor table with the film actor table that relates films with actors. And after that, I just put in the where clause the film ID I want. And the joining column is actor ID, is the column that joins film actor and actor tables. So if you look at the plan, we have one sequential scan on the actor table, and we will put the results on a hash map. It's a bit different of a bitmap. The hash map, it has a hash that is calculated with the result of the sequential scan in a table, in a temporary file that can be kept on memory or on disk. For the table film actor, we will make a sequential scan too. And actually, we filter the film ID. As we told in a non-efficient plan here, we have to scan the whole film actor table to filter out just one ID. So it's not efficient. But here is for the sake of the example, we'll show you that the second sequential scan plus filter, we store the results in a second hash map. And then we make what we call a hash join. Is that we will compare both hash maps for the two sequential scans and eventual filters, and we compare those, and we make a merge, and it gives you out this gives you out the results. One thing that's interesting to understand is that the cost to retrieve the first row is quite low, like almost 0, and the cost to retrieve all the rows is 104 IOs that we have to do in this. And then, sorry, in the next slide, we can see that I created indexes on the field actor ID in the table actor and the column film ID in the film actor table. What changes here? Like if I read the plan from below to up, I see that we have to make an index scan in the actor table using the actor ID. And I will make an index scan in the film actor table with the condition film ID equals 1. So you will see that the index scan is quite fast and quite less expensive than a sequential scan, because I have to scan just a small part of the table and a small part of the index to retrieve around 10 rows. And then from the actor table, I will retrieve like 1 row by actor. So there is just 1 actor by actor ID. And with those index scan, how I join them together, I make what we call a nested loop. So if you already make it programmatically, imagine that you have 2 tables, 2 arrays in memory, and then you loop from the first array, you loop over the second array to retrieve the results that match. That's how Postgres does it. It will use 2 index scans and loop over one over the other to retrieve the results. And this is quite fast, and this is quite less expensive, like 1/10 of the cost of the sequential scans that we did before. And Postgres can do that on the go. Actually, it doesn't use any memory space. We don't need temporary files for that. We just loop over one result over the other on the go. And the cost for the first row is still quite low. And the cost for all the rows is a lot cheaper than the first example. So that's why indexes are important when we have queries that retrieve just a small part of the row of the tables, just a small quantity of rows from the table. And here, I made the things a little bit complicated for you. I just joined another table, the table film. So we have film actor, and actor joined together. And why I need here to use that is because I want the release year of the movie, like the year, I want all the movies that were released in 2006, and I want all the actors that have last name as Johansson. And then I will count the results. I don't want to display the results. I want just to say to the user how many movies correspond to this situation. So how we read the plan right there, we actually have the index scan on film, and actually we filter out the year because I don't have an index on year. So Postgres decides to filter out the year, and then we can index scan film actor to retrieve the actors that correspond, and then a sequential scan on actor because I don't have an index on last name here. So I will sequentially scan and filter out the last name that correspond to Johansson. And then with nested loops, I will try to loop over all the results step by step. And in the end, I will aggregate to make the counting. So I don't have a way to make it on the fly. I can't do that on the go. I have to store the results somewhere to count over that. That's why this plan is a bit special. Like, I try to make it graphically so it's easier to understand. So for the table actor, as I said, I don't have an index for the last name, so I make a sequential scan and I filter out. I join that with film actor, and I can index scan because I have an appropriate index. So I will loop that on the go, one result over the other. And then to join out the film table that I can index scan because I have the appropriate index, and I will loop over the first result. And all those loops can be done on the go without any problem. But when I need to aggregate, I have to take all the results, put it in some space in RAM or disk to get the counting. It's another algorithm. It's another access method. So I need some RAM space. That's why I'll get back to the previous slide. That's why the cost, the initial cost, is not zero anymore. I need to run all the plan that is below the aggregate to aggregate at the end. This is one thing that I can only do at the end. So the cost of retrieving the first row or all the rows for you is exactly the same. I just have one row as a result. It's the count. But to have this count in one row, I have to retrieve in the latest loop, the outmost loop in the plan, I have to retrieve 82 rows of data for you. And that's it. I take these 82 rows, I put that in a temporary space in RAM or disk, and then I can count it out.
All right.
So, okay. And I have a last example of sorting, how we can do order by. So the first example is just the first select without any where clause, without any filtering. I would just try to order the name of the actors by last name and first name in this order, respectively. Without any index, what we do is a sequential scan of the table, as we saw before. And then we will make a quick sort, is a sort method, and it's done in memory. And the explain analyze shows me how many memory it needed, how much memory it needed. And exactly as an aggregate that we saw before for counting, I need to put that in memory, and the cost for the first row and the last row is approximately the same, because I need to put all the rows in memory to sort them out and then display the results for the user. If I create an index on exactly this pair of columns, and I do exactly the same query again, we have what we call an index scan in this index that I just created. And as you can see, the cost for the first row is 0 because I will try to find the first row in the index. I don't need memory here. And the cost for all the rows is 11. It's almost the same cost as the sequential scan. Why is that? How is that possible? The index are always faster than sequential scan. Actually, no, it's exactly the contrary. To scan an index entirely costs a little bit more than to scan the table sequentially. If you look here, the sequential scan cost in the first select is 4 for all the rows. The sequential scan on actor is 4. And the index scan for all the rows is 11. But why Postgres decided to go to the index anyway? Because it needed memory, and to sort data in memory, that has a cost. So here, when I scan an index, I use a little less resources scanning the index entirely to give you the results in order, because I don't need memory. I don't need to loop over the memory to try to find all the rows. And there is a last example, is if you look at the query, it's almost the same, but not exactly the same. The second query, I do a select star from actor. And the last query, I precisely included just 2 columns, last name and first name. Those 2 columns are exactly the same columns that are present in the index. So Postgres is capable of doing what we call an index-only scan. Actually, all the data is present in the index, and I don't need to match and find and match corresponding rows in the table file. So this is a little bit faster than to take the rows from the index plus the table. And Postgres can do that for us today in the latest versions from 9.6, I think it was made available. So if you have these special situations where all the columns you need are included in the index, don't put star here, or don't put columns that you don't need. Put only the columns that you need, and Postgres will use the index-only scan. It's quite fast if you have large tables. What we learned here? We have several ways to join datasets, as we saw that before. Some of them need memory. Some of them need temporary files if you use a lot of memory. Others can make it on the go, like nested loop. Some operations can only be made at the very end, like sorting without indexes, or summing or counting. Index sometimes have all you need, and it can be super fast. And you can influence the plan with your decisions to make new indexes, or depending on the columns you put on your select.
So there are other access methods we didn't talk about in this presentation. As I told you before, we couldn't address everything within an hour. And we hopefully do that later in the year. What you can remember is, like, as you could see with Flavio, with the example he explained us, is that the queries can be very complicated, and so the plans will be complicated as well. We put in the appendices of these presentations some tooling, query plan tooling, that you can use to display graphically your query plans in a more sympathetic, let's say, way than the command line, if you prefer. And we put a lot of references that we have used during the presentation. Okay. So, Flavio, let's together also get in touch. Hopefully later on. I personally learned a lot of things during preparing this presentation. It was not only fun doing it with Flavio at leboncoin, being at Doctolib, but I also learned, like, specifically a lot of things about Postgres. So I'm very glad so I was able to talk to an expert. And hopefully we'll do another presentation later on during the year, as I said before. What about you, Flavio?
Yes, I hope so. I hope so. We can go a little deeper in the subject. I think there are a lot of things to talk about this. We just showed you the most basic access methods and so on. We can make more complicated queries. We can put another access methods. There are ways to make plans that are not optimal. Like today we have the just-in-time compilation. There are lots of things that we can talk about. So keep in touch. I think we can make it again. And I really appreciated the time together to talk with Olivier. And it was nice because I was a Doctolib. I used to work at Doctolib. It was 2015, I think, that I worked there. And I miss you guys. So it was very nice. Make this presentation for you, and I hope you can do it later again.
And now we have like a recording and some documentation for new journals. So hopefully is going to be great for those people. Let's maybe take some questions. I don't know.
Yeah. I think I'm muted. No.
Yeah.
Okay. Thanks a lot, Olivier and Flavio. That was very interesting. I, for one, am very much looking forward for part 2 of this. So thanks. Now, to the questions. I will take them in chronological order. First off, at slide 11, Franklin was asking, are there any reasons to change the cost in the config files?
Yes, actually, yes. For example, by default, the random page cost, when you scan an index, it's random. The cost in the config file is 4. This is approximately 4 times more expensive than to scan a page sequentially. This was real when we used to have spinning disks, magnetic disks to use on the database. But today we have SSDs that are almost the same cost to scan a page randomly or sequentially. Or if you have a large storage array that you have a lot of cache memory, all those pages will always be read at the same cost, so you can modify this cost. And you can put like 1 for the random page cost and make tests again, and you will see that Postgres will have a tendency to use more indexes than doing sequential scans. It will really modify the behavior of your database system, and quite a lot. You can see that in quantity of I/O that you're using, and quantity of memory you're using, and also quantity of CPU you're using. Everything has a large impact on that. But make tests before that. That's why we told you that you can put set on your session. You just open your session in any client you want to, PSQL, PG Badger, PG anything, or actually PG Badger, sorry, is dbeaver. There are a lot of clients that you can use to query your database, and make a test. Put set random page cost equals 1 and remake your explain and see what happens, if it's faster and if it uses less resource, and you can see that. That's it for this question.
Okay, thanks. Next question from Prabs at slide 12 was, I'm sorry, yes, slide 12. Why are the actual and expected costs so different on the example you had of the explain analyze?
So I don't know, I mean, what is really in that. So in this example, if you can show, I don't know.
It was slide 12.
Yeah.
I'll try to display the nice slide 12.
But the results are not really different. What we can see is that the explain would give us first the cost and the access method, the sequential scan. And it estimates as well the number of rows to be returned. So one was 3,250 rows, and the actual numbers were 3,261. So the 11 difference coming from because it doesn't know the statistics. So I mean, it didn't know how many rows to be returned exactly, because it didn't have any stats. But by running the query, obviously going through all the rows, the actual number of rows is determined. And so I'm not sure why
actually the cost is estimated over the statistics. And Postgres, it won't scan your tables entirely to know exactly how many rows you have. How many rows you have. Actually, it will make what we call like samples of the table or the index, and it will try to estimate how many rows you have. That's why there's a very little difference between the estimated counting of rows and the actual number of rows. The first one is based on statistics, and the second one is really the result of the query. So to make a plan, I want to run a query. It's too expensive to do that. So I run the plan over statistics. That's why it's a little difference. It's normal. It's like that.
But it could be very different if your statistics are all wrong, for example.
Yeah. If your statistics are not up to date, you have a large difference, and then you have to run analyze before running your query again.
I think also maybe the question hinges on the difference between the expected cost and the actual time. You told us yesterday that there is no such thing as an actual cost. I think this is also part of the answer.
No, actually we have an actual time and an estimated cost. That's it.
And how do they relate? Is it like proportional or something like that?
It can be proportional. Like if you know how much time your disk takes to return one page, it's a little bit proportional, yes. But when you have some memory to make sorting or aggregation, then it will differ.
Okay, thanks. The next question on slide 25, Jeremy was asking, how can a bitmap with a single condition be faster than just an index scan?
Take that. Actually, when you have a lot of results, actually it's not the amount of condition that is related here. Is the number of rows will match the condition. That's why Postgres will decide when to use an index scan or a bitmap scan. If you have a lot of results, intermediary results, you can't do that on the fly. Like you can't just index scan and give the result to the user. And if you have another operations to do inside the results, like an ORing two results or joining two tables together, you can make bitmaps because it's faster using a CPU to relate two bitmaps, for example. But if you have a very small amount of results, you can use just nested loops.
Okay, but what about the case where there isn't a join with the example with the letters? When choosing the letter B, I think the one that was not very frequent, but still more than maybe 2%, we were using a bitmap scan. It was a slide 25.
I made the bad manipulation, sorry. So 25, this one.
Okay. Yes, so there isn't a join, yet we are using a bitmap scan.
Yeah. In this case, we use a bitmap heap scan because we have what we call the recheck condition. Actually, Postgres will, in the latest example with the letter B, Postgres will just use a condition in the index, and it will really fast will give you back the results. When you use the example of the letter P, it will filter out. And when you use the example of letter A, you have to recheck your results to see if they match. So the easiest way to do that is to put the intermediate results of the index scan inside a bitmap, so you can recheck using the CPU in the memory. That's why you have the intermediate step. It's quite faster to do that in memory than on the fly with an index scan.
Okay, thanks. Next questions are both from Prabs on slide 29. First one was, will a query dependent on a non-indexed column always using a sequential scan?
Yes. Yes. Almost always.
Okay, that was clear. And the second question was, why can't a transaction auto-clean non-accessed dead rows by itself?
Because transactions are independent. One transaction doesn't know what happens in the parallel transactions. In Postgres is a multi-process engine. So when one transaction is happening in one connection, there is a backend process of Postgres that is responsible for handling what happens in this transaction. A second transaction will run in a separate process that will loosely communicate with the first one. But the first transaction that arrived doesn't care what about is happening in the parallel transactions. It will be very expensive to check if there are other transactions running at this point. So to be as fast as possible, we do the things independently inside the transaction. And we say to the other transactions that the rows will be dead in a certain point in time. So I say, from this transaction number, that is an internal counter inside Postgres, from this transaction number on, those rows are dead. So the other transactions are responsible to check that for you, not the transaction that is running. Otherwise, it will be too expensive to check between 100 transactions running if all of them are finished, and then suppress the row that is already dead. Another thing is that when we are finished, if there are transactions that arrived before us, they will still see the old version of a row, and we are already finished. So my transaction is already finished, and I just will disconnect, for example. So I don't have anything to do anymore. And the backend process that took care of my queries will disappear. So the dead rows are left behind. And that's the responsibility of the vacuum process to check if all the transactions that need a certain version of a row is still needed. And that's why the auto vacuum is necessary, and that's why it's quite a heavy process running. It has to check everything. It's responsibility to check everything, not for a backend process that has to be fast and optimal.
Okay, thanks. We have one last question, unless others pop up, from Yang, who asks, from my understanding, bitmap is the same ID as a Bloom filter. What do you think?
I don't know what is a Bloom filter.
Neither do I.
I might be able to answer that one. So there are some of the same ideas. So Bloom filters, they're just a way to have a sort of set. You can put elements in it, but then you can only know whether an element is probably inside or maybe the reverse. But it works with bitmaps and operations on bits and on hashes. So bitmap filters do operate with bit fields and binary operations between those bit fields, but there is no, it doesn't use any sort of hashing, it doesn't use any sort of cryptographic functions. So some of the basic IDs are the same, but no bitmap filters are not based on Bloom filters at all. And yep. Fabrice says that it can have a false positive, but no false negative. Thank you.
Yeah.
I just put in the chat a link to the Bloom index that exists in Postgres. So actually, the name said me something. So I just checked the documentation. We have a Bloom filter, and there are sometimes this kind of filter is very useful. So I'll give you some time to read that if you want to, and in the next presentation maybe you can talk about it.
All right, that would be interesting. Well, if we don't have any questions, I think we are done. So thank you everyone for attending. Thank you, Flavio and Olivier, for your time and your knowledge. And well, see you most likely next time for part 2.
Yeah. Thanks everyone, and see you next time.
Yep. Bye-bye.
Thanks. Bye everyone.